In this video, I'll be discussing enthalpy and how to calculate it for a reaction. So enthalpy, symbolized by the letter H, is one of the major state functions of thermodynamics, and it represents the internal energy of a chemical reaction, and sometimes you hear it referred to as the heat of a reaction. There are two major ways to calculate the enthalpy of a reaction. You can use standard enthalpies of formation for compounds, and that would use this equation up here, the top one, where you take the sum of the enthalpies of formation for your products minus the sum of the enthalpies of formation for your reactants. And you can also use the bond energies of the bonds found in the compounds in your reaction. And to do that, you would use this equation down here, the bottom one, where you take the sum of the bonds broken in your reaction, which is the reactants, minus the sum of the bonds formed in your reaction, which is the products. One thing I would like to point out that's very important is the fact that for elements in their natural form, their enthalpy of formation is equal to 0. And what I mean by elements in their natural form, that would be things like O2, H2, F2. Elements like that, when they're in their natural form, their enthalpy of formation is 0 kilojoules per mole. And that's very important and something to definitely keep in mind. So here we have an example question. Calculate the enthalpy of a reaction for the following reaction using both bond energies and standard enthalpy values. So we're going to use both methods to calculate the enthalpy of reaction here. And then we're going to use our value for delta H to determine whether the reaction is exothermic or endothermic. So first we're going to start with using the bond energies to calculate enthalpy of a reaction. And I should note that we are doing two different methods here. They will give you two different answers, and that's okay. Doing it with the bond energies will give you a different value for delta H compared to doing it with the standard enthalpies of formation. So if you get two different answers, that's fine. You usually should. So let's go ahead and look at how to calculate the enthalpy of a reaction using the bond energies. So the first thing I would do when I'm going about calculating enthalpy using bond energies, which you can also hear those referred to as bond enthalpies. So bond energy and bond enthalpy means the same thing, just to let you know. But the first thing I always do is I always try to think about all of the bonds that are present in each of my compounds in the reaction. So I'm just going to go through each of these compounds one by one and kind of look at the Lewis structure of that compound to determine what types of bonds I have and how many of those bonds I have for each compound. So starting with F2, if we draw the Lewis structure for F2, it's fairly simple. You just have a fluorine single bonded to another fluorine. And we have a chart up here. And all of these bond energies and the standard enthalpies of formation are tabulated, which means, they're all these values are known and they're established in tables that you can look up. And I wouldn't expect you to memorize the numbers for these. You either look them up or they're provided for you, but they're all tabulated. So if we go in our first chart up here and we look at the F to F single bond, the energy associated with that bond is 154 kilojoules per mole. And here we have two of them. So we're going to have two of those F to F single bonds. So when we go through and do our calculation, we're going to take that into account by multiplying that 154 by 2, because there's two of them. Next we move on to water, the H2O molecule. If you look at your Lewis structure for water, you'll see that we have an oxygen that's single bonded to two hydrogens. In our reaction, we have two water molecules, so you have to take that into consideration. One molecule has two oxygen to hydrogen single bonds, and if you have two molecules, that means you have 4 oxygen to hydrogen single bonds here. Same thing over here with this HF. HF is a very simple Lewis structure. It's just hydrogen single bonded to fluorine. But here, because the coefficient is 4, that means we have 4 of these H to F single bonds. And for O2, if you draw your Lewis structure for O2, it's just oxygen double bonded to the other oxygen, and that means we have 1 of those oxygen to oxygen double bonds. So now that we've established all the bonds in our reaction, let's go ahead and write out our equation for calculating the enthalpy of reaction here. So setting that up in your equation here, you're going to have your enthalpy of reaction is equal to 2 times the bond energy for the F to F single bond plus 4 times the bond energy for the O to H single bond, and that's for your bonds broken for your reactants, minus the bonds formed, which would be 4 times the bond energy for the H to F single bond plus the bond energy for the O to O double bond there. So if you take the first part over here and add those together, you should get 2,176. And if you take this second part over here in brackets and add them together, you should get 2,755. Subtracting those two, you should get negative 579. And so that means that using bond energies, you calculate the enthalpy of reaction as negative 579 kilojoules per mole. And the units are really important. If you leave off the units, your answer will be wrong. And for enthalpy at least, the units are usually kilojoules per mole unless the question specifies otherwise. Always make sure you check and see what units the question wants your answer to be in. Most of the time with enthalpy it'll be kilojoules per mole, but always check and make sure. So now that we've calculated this doing the bond energies, let's go ahead and calculate it using the standard enthalpies of formation. So now let's go ahead and calculate the enthalpy of reaction using the standard enthalpies of formation. And for that, we're going to look at this first equation up here. And we're going to focus on the numbers coming from the second chart down here. And the reason only 2 of the compounds are listed in the second chart is because the other 2 compounds in our reaction are in their natural state. F2 is a diatomic atom in its natural state, so its enthalpy of formation is 0. Same thing for O2. It's in its natural state, so its enthalpy of formation is 0. Always check your reaction and see if you have any compounds that are in their natural state. You can just cross them out because they won't be factored into the calculation of your reaction enthalpy. Also, always check and make sure your reaction is balanced because those coefficients out front are essential for correctly calculating the enthalpy of reaction. So first off, we want to look at the sum of the enthalpies of formation for our products. And the only product we're interested here is hydrofluoric acid, HF. And there's a 4 out front of it as the coefficient, so we'll stick a 4 here. And we're going to take the value for the enthalpy of formation, which is negative 335.35. And like I said, we can just ignore the O2 because it's just 0. And we're going to subtract our reactant of interest, which is water. And there's a 2 in front of water, so we'll stick a 2 here. And the value for liquid water, and that's another important point too. Always look at your state of matter for your compound, because different states of matter for the same compound have different values for enthalpy of formation. For example, here we have liquid water, and that's the enthalpy of formation for liquid water, but gaseous water, for example, would have a different enthalpy of formation. So always check and make sure you're getting your state of matter correct when you're looking up your value. And that's going to be negative 285.83. And we're not interested in F2 because it's just 0. So we'll close bracket. So go ahead and do the math here, and this will give you the enthalpy of reaction. And so therefore, using the standard enthalpies of formation, your enthalpy of reaction should equal negative 769.74 kilojoules per mole. And you'll notice, again, we got 2 different numbers doing the 2 different methods, and that's perfectly fine. So now we have to make a judgment call over whether this reaction is endothermic or exothermic. And there's 2 different scenarios for your value of delta H that will let you know if your reaction is exothermic or endothermic. So if your value for delta H is less than 0, which means if it's negative, so if your delta H is negative, then your reaction is going to be exothermic. And if your delta H value is positive, that means that your reaction is endothermic. So here we had our enthalpy of reaction is equal to negative 769.74. And in the other, when we did it with the bond energies, we also got a negative number. So therefore, in this case, your reaction would be exothermic because your delta H value is less than 0.